We're going to start reviewing some more code, and obviously one of the biggest important functions that we have with a binary search tree is inserting the node into the tree itself. Now remember, there's always a game plan that we start at the root and we use that to basically traverse to the rest of the tree to find the spot that we need to place our newest node. Now there's several scenarios that can happen here. Is first adding the first node into the entire tree, so the tree is empty until we add our first node, and I'm going to show you that here in a moment. Then adding a left child or a right child. Those are your three scenarios that we have. Now in the code that I give you though, there's two actual insert functions. The one is to start things off, and it's called a bootstrap. And this algorithm starts with us basically saying, okay, here's the value, but it's a delegator, so it says here, okay, here's a new value, and here comes the root that you need to glide down to put into the right spot. The second function is the one that actually really does the work. It traverses the tree, it compares the values from what's in the tree to the current value in the node that you have, so it knows exactly where to go, and it does all the connection and the returning of a new node. So let me show you what that looks like. So in our example of code, notice the bootstrap first. That's always going to be listed first, frankly, for me, the way I set it up here to alleviate some confusion. But notice the bootstrap really doesn't do much. The only thing it does is call another function of exactly the same name. Now notice the difference between the two functions of insert. There's the first one, which is the bootstrap, that has just one parameter, and that's the one that you and I are going to call all the time, whereas the second one is a little bit meatier. Again, you'll see that these codes that I'm showing here are incomplete. I'll show you that later. But they have actually two values that go in them. First is the actual value or node that we want to place into the tree. The second one is the actual root of the tree that, again, we start from, and then we move down through the tree. Here's the other part, though, is that it's really important to understand that every time we move down the tree, that item that we move down now becomes that root of the subtree. So it's really important to make sure we understand that. We're also going to show you how we would glide left or right, which is real easy. That's the good news. But for right now, the only thing that I'm showing you is scenario number one, where everything is totally new, the tree is completely empty. So that's why we look at the if statements inside of the function. And if the root happens to be completely null, then we make that root our new binary node of whatever data type that we want, and we set the value, and we set the left and the right parameter to null. Now this constructor, by the way, that you see here came from the binary node class that you and I have already talked about. In our next scenario, we're adding a new value to the tree. We already have M in there. We're about to insert B. And B is going to go ahead to the left-hand side. Notice that I've only really added a line or two to the previous set of code here, but you'll notice the important part, and that is how we actually compare the value from the element itself that we're about to place in, or node, to what's in the tree. Now, in C++, we can get away with using an overload, but overloaded operator, that is. But in C++, we use the compare too. Now again, both of these, no matter where they are, we had to use the complete class profile and have those individual items in our individual element, like employee, like student, or something like that, in order for us to compare each of the different students or employees within the tree. So these do not come natural. We have to make sure that whatever our base objects are going to be placed into those binary search trees, that they are coded to do some type of comparison. And we would have gone over that already before we got to this part. By the way, there's a dirty word that pops up, and that's recursion. Is that what if we had to keep going left? Let's say this was a massive tree, and we had to keep going left. Well, here's the scary part. If you look at that if-else, it calls insert again. That's the recursive part where it's saying, okay, here's the value. Now the new route is going to be wherever I am and to the left. And that's how it moves throughout the tree to, well, basically put our node into the right spot. So this is recursive. Be careful about that. Because of the recursive properties of this function, this also takes care of when we finally land in a spot in a tree. Now remember, that new spot that's always going to be null because there's no value in there quite yet. So eventually, once we make our left turns and then we land in that spot, then we create our brand new node and place it in that spot, well, to complete the rest of our tree. Below is the entire code. There really isn't much except for now the adding the right-hand side to the overall function. But pause here so you can look at the recursion, making sure that you understand that it will eventually stop at that if case, and go from there. Also make sure that you understand the overloading of the comparison operators depending on the language, and making sure that everything makes sense to you in this kind of fashion, and recursive call as well.